Hello friends. See, in previous video what we have seen is that what is binary search tree and how to create a binary search tree using the basic properties of binary search tree. So second thing is we have traversal. There are three type of traversal, that is in order, pre-order and post-order. Now in this video we will discuss uh, the other operation that we can perform on a binary search tree, that is search operation, insertion and deletion. So just see this. Assume that we have a binary search tree where the root is 48. All the value less than 48 is on the left subtree. All the value greater than 48 is on the right subtree. And just assume that if we have to search a value and the value is equal to 14. So how it will be done? First it will compare with root. You can say that uh, 14 less than 48, so it will go to left. Again 14 less than 37, it will go to left. 14 less than 20, it will go to left, and here 14 equal to 14. So you can say the search is successful. And you can observe that total how many comparison I have done first comparison at this node, second comparison, third comparison and fourth comparison. So total number of comparison in this case is 4. So you can say that within 4 comparison you come to know that whether the 14 is available in this tree or not. So you can see the running time of this searching algorithm is nothing but you can say there are two cases that in general the time complexity of search algorithm in BST is order of h, where h is height of a tree, height of a tree. Even we can say this is order of log 2 and also almost same. We can say either order of h or we can say order of log 2n is the search time complexity of a BST. But if we have a balance, but the problem is that suppose if we have a tree structure like this, for example 8, 7, 6, 5 and 4. Just assume that this is a tree, and even it is also a BST because all the value less than 8 is on left, all the value less than 7 is on left, so it is also a BST. And suppose if I have to search 4, now total how many comparison will be there? 1, 2, 3, 4 and 5. So you can say the number of comparisons are 5. And how many elements are there? Again n is equal to 5. So actually this tree is it is also called a left skewed tree. It is also called a left tree because all the nodes are on its left. So if your tree is unbalanced like this one where all the nodes are on left side, so in this case the time complexity will be order of n, where n is the number of element. Similarly, if you can see suppose 5, 6 and 7, in this case all the nodes are on the right side. And suppose if you have to search 7, how many comparison? First, second and third. So again it will take 3 comparison and number of elements are also 3. So time complexity is order of n because it is also an unbalanced tree. So this is called right skewed tree because all the nodes are on the right side. So the concept is that if your tree is balanced, just if you can see we have enough number of nodes on left side as well as on the right side, In that case, if the tree is balanced, then the time complexity is order of h, or you can say order of log n. But if the tree is unbalanced, like this one or this one, in that case, the time complexity will be order of n. So this is the worst case, you can say. This is your worst case. So this is the overall idea of how the searching is done, and the main objective of binary search tree is to reduce the search time. Main objective is to reduce search time to order of h or order of log n. So this is what the search binary search tree says about the complexity. Now the next one is, let's see, insertion. And again, in insertion also, the worst time complexity is order of n. If your tree is unbalanced, whether it is a left skew tree or it's a right skew tree, in both cases the complexity will be order of n. For example, just see 4, 3, 2, and suppose I have to add a new value that is called 1. So where the 1 will go? First it will compare over 1 less than 4 this side, 1 less than 3 this side, 1 less than 2 this side, and then it is going to add over here. So how many comparison it has done before inserting 1? First, second, and third. And how many element was there? 3. So again, in insertion, if your tree is unbalanced, so the time complexity will be order of n. But if your tree is balanced, like this one, and suppose I want to insert a value that is called 7. So first comparison with root, 7 less than 70, come to left. 7 less than 17, come to left. 7 less than 8, so it will be added over here. So total how many comparison I have done? In this case, when my tree was balanced, 1, 2, and 3. So you can say the time complexity for insertion is again order of h. The h means the height of the tree, or even you can say order of log n also, meaning remains same. So this is how the insertion take place. Okay, next operation that we can perform with binary search tree is deletion, and again the time complexity of deletion in BST, if it is a worst case, order of n, and if it is a general case, that is order of h, where h is the height of the BST. So time complexity of all the three, searching, insertion, deletion, everyone is having same order of n or order of height h of the binary tree. See, but the deletion has some cases. For example, suppose the node that I want to delete has no children. It's just like a leaf node. So like this, suppose there is a node called a, it has no left child, no right child. So what we have to do is we have to just delete this node. So simply we have to remove this. We will take one examples later on. Second part is, suppose that we want to delete a node with one child. Now one child means, just assume that we have a number called 4 and it has a right child that is called 7, and suppose we have to remove this node that is 4. What should we do? We simply copy this child node over here. So instead of 4 it will be 7, and then remove this node. So finally what is the result? We will have only one node that is called 7. So always remember, if there is only one child either on left or on right, just copy that child to the deleting node and remove that child, that is 7. And case 3 is, just assume that if we have a node 8 and it has two childs, 6 and for example 9, and we have to remove this 8. So if we have to remove a node 8, either I can copy the in order predecessor of 8, who is the in order predecessor? Okay, can you find out the in order? So it will be 6, 8, 9. That is the in order of this tree. So if you have to remove this 8, either you can copy predecessor of 8 at this place, like this. So it will become 6, and then just remove this node, or you can copy the in order successor of 8, that is 9, who comes after 8, that is 9. We can copy it over here and then remove this node. So if there are two nodes, then we have to follow the in order predecessor or successor of the deleting nodes. Let's have this example, a very simple one. So just see this case. Suppose this is case number 1, when we have no child, and suppose I want to delete a node called 10. What will happen? We will compare 10, that is greater than 4, so it will come to right. 10 greater than 9, so it will come to right, and here the node matches. So if this deleting node 10 has no left child or right child, so we simply delete it. And finally, what the tree will you get, what the tree you will get 2, then it will be 9, then it will be 7. Now this is your resultant tree. And again, if you suppose you want to delete 2, suppose I want to delete this 2, since 2 has no left child, no right child, so what we have to do, simply we have to delete it. And what is the resultant tree? 4, 9 and 7. So this is the tree. So a final idea is that after deletion it should remain a BST tree, and it should follow all the properties of the BST tree. Let's have another example. Just assume that this is the case. We have set of nodes and it is a BST. So after deletion also it should be a BST with all the BST property, and just assume that I want to delete 10. So the question is, this 10 is a deleting node and it has one child, that is 11. So what should I do? Simply I just copy the child of 10 to this node. So instead of 10, what will happen? It will become 11, and then remove this child. So what is the final tree? 4, 2, 9, 7, okay, and then 11. Now this is your tree, and again if you see, it follows the property of BST, so it is okay. Now so this is what we have, that if there is only one child, how can I delete it? Just copy this thing. Just assume that if it is like this 6, and suppose if I have to delete this node, delete 7. So 7 is having only one child, that is the left child. What should I do? I just copy this 6 over here. So instead of 7, it will become 6, and then remove this child. So what is the final answer? 4, 2, 9. On 9 it is 11, and on left it is 6. So this is how the deletion takes place when it has no child, this case, and when it has only one child. Now the final case is, just assume that if we have two children, this is the case, and suppose that we have to delete 47. This is my deleting node, and as per the rule, this deleting node has two child. One is called left child 45, and right child, that is called 50. So what the rule says, that if the deleting node has two child, left and right, you have to find out the in order successor of 45 and or in order predecessor of 47. So the in order successor of 47 is 50, in order predecessor of 47 is 45. So basically, if you draw the in order, it will be 4, 7, 10, 15, 18, 20, then it is 30, 40, 45, 47 and 50. And suppose what I said is that you have to remove 47. So who comes before 47? That is 45. So I can copy 45 over here. So instead of 47, it will become 45 and then remove this node. Very simple. So what is your final tree? I can draw over here. So you can see 20, on right it is 40, on right it is 45, on right it is 50, then on 40 it is 30. Now left subtree remains same, 7, 15, 10, 18 and then again 4. So this is the resultant tree. So as you can see, after deletion it should maintain the property of BST and still it is a BST. So this is what the basic idea of this one. Now we can do one more deletion. Suppose I want to delete this 7, this one. So what should I do is we should replace the predecessor of 7. Who is the predecessor of 7 is 4, or who is the successor of 7, that is 15. So either I can move successor over here, so it will be 15, sorry, not the successor of 7 is not 15 but it is 10. Just remember, successor of 7 is 10 in order successor, so it will come here and then we remove this node. So what is the final picture? 20, then on left it is 10, on left it is 4, then on right it is 15, on right it is 18, here it is 40, 45, 50 and then this is 30. And after deletion it follow the same BST property, that all the value less than 20 is on left, all the value greater than 20 is on the right. So this is how the deletion take place in BST tree. Always remember that it has 3 cases, and on the basis of case we have to decide how to delete a particular node. Thank you very much.